This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning at this ungodly hour. This week I'm going to teach lecture 14 and 15. So Gavin is away, so you're stuck with me. Maybe you have the misfortune of seeing me again next Monday as well. So in case you need an incentive to pass this subject, I will be the one who will be teaching it next semester. So use this to incentivize yourself to study more. Today I'm going to talk about scheduling, right? Last week you were introduced to multitasking. So really it helps if you spend some time thinking about multitasking to really understand why we need scheduling. The main chunk of the slides are based on chapter 12 of your textbook, The Embedded System, the Cyber-Physical Approach by Edward Lee and Sandy Seshia. And then based on this other book by Giorgio Buttazzo. And if you need extra bit of information, I've included these two references as well. And hopefully by now you know that any Springer book, you can legally download it from the library, Embedded Systems, library, University of Melbourne Library. So maybe it is worthwhile to download these books as well. Just to get a feeling, how many of you have looked at the textbook? Okay, this is shocking, right? Because you will never learn anything from the slides alone, ever. So whenever you want to learn, you have to go to the source material. So I really recommend that you go and have a look at the textbook throughout. Hopefully you should have done it earlier, but you haven't done it, it's fine. Go and look at least about these lectures and the future lectures. All right. Now, to just put things in context, let's just think about problems in the context of microkernels. So what is a microkernel? It's in the title. Usually a small, custom-built operating system that handles tasks of an embedded system. Okay. So what it really does, the responsibilities of a microkernel include, it's not an exhaustive list, but these are the main responsibilities. The responsibilities include scheduling of threads and processes. So thread is this word that is a bit used to mean all sorts of things. So one thing that it might mean is a task or an imperative task. Can someone tell me what an imperative task is? A piece of C code that tells the computer to do some calculations is an imperative task, for instance. So these threads really refer to these sort of tasks. So scheduling is a part of it. So really when to start a task and when to terminate it, and really regulate the timing, when to terminate, how long should we let a task to go on, when should we stop it, when should we switch to another task. It does something else as well, which is really related to being able to carry out those tasks, synchronization. And again, you've seen these in multitasking. It's really about those mutually exclusive locks, semaphores, etc., etc. And then it handles input and output, interrupt handling as well. But if you think about all of these things, all of them enable us to be able to carry out tasks, to collect measurements from an output sensor, do computations, to set a reference to something that we are controlling, for instance. So all of these things are really to capture that. There are a bunch of other things that a microkernel does, really an operating system does in general. It does memory management to make sure that we have different stacks so that we don't have segmentation problems. It handles file systems, so persistent storage. So when we store something in the file system, we can recover it later. That's the persistent storage. So it's not just, it doesn't disappear. It's not volatile. It handles networking. For instance, it implements a version of TCP/IP stack or any other networking protocol that we are using. It handles identity management, so user management and security as well, in terms of the user security and the kernel security. We are not going to talk about these things in details, but it's good to be aware of it. Now, scheduling. One valid question is that when do we need scheduling? The answer is that. Can someone elaborate? Anyone? Why do we need scheduling? Very tough crowd. Okay, let's go through the first three lines. If I am carrying out different tasks, multiple tasks, for example, I have to read output of some sensor, I have to do a bunch of calculations, I have to set a reference. Each of these things are different tasks. And I don't have dedicated processors for each of these tasks. And I only have, for example, one processor to handle 5 different tasks. I have to allocate some time schedule, for instance, for each of these tasks. I have to assign which task should I at any given time, which task I have to handle. I have to determine, in terms of priority, which task has a higher priority or a lower priority. And I have to guarantee that I meet some timing guarantees as well. Okay. Now, timing is very, very important in embedded systems. So just a question, I hope you've thought about it before. If you build a system using Raspberry Pi, is that system, let's ask the question differently. Do we have any timing guarantees when we use Raspberry Pi? Why not? Vigorous shake of head.
Because it runs like a full Linux system, which doesn't provide any real-time guarantees.
Good. Because it's a full OS, like your tablets or your laptops. There we don't need to worry about delivering a task at a given schedule. We don't need to worry. It doesn't matter if something is delayed 1 second or not. So what is an example of an application that we should worry about timing? Well, just for dramatic effect, all the applications that if you mess up timing, you're going to kill people. Aircraft. Autonomous cars, if they ever happen. My view is that they won't, but that's a different thing. So, all the critical applications, we have to have timing guarantee. So I cannot watch some hacky video on YouTube and just put something together and call it an embedded system. That's garbage. And that's really a disease that has infected a lot of engineers, turned them into technicians. So we have to be careful. Timing is very important. We have to be able to handle it. So any scheduling that I'm going to talk about will be about, we'll have that timing element as well. Now there are two ways of scheduling, static and dynamic. So one way is to, when we are putting together the system, come up with a full recipe of when to do which task at what time. A priori. That's a static. We make decisions at the design stage. Which task, is going to be carried out when, by which processor. Which task has the higher priority. And then we can always contrast it to dynamic scheduling as well. So we determine the assignments, the ordering, and the timing of completing tasks on the fly. As tasks arrive, we determine what's going to happen, which task needs to be done next, etc., etc. And then I said there are combinations of static dynamic designs as well. And I put in brackets meaningful, question mark. So I'm going to propose a combination of static and dynamic choices for assignment, ordering, and timing, and then you tell me if it makes sense or not. So I'm going to say I'm going to do timing dynamically, I'm going to do ordering statically, so in design stage, and I'm going to do the assignment dynamically as well. Is it a meaningful way of designing a scheduler or not? Show of hands. Who says it's a meaningful combination? Okay. Who says? Okay, one person. Great. Someone with an opinion. Who says it's not a meaningful combination? One and a half. Tentative. You dropped your hand. Okay, good. So the rest of you don't have any opinion? Or you're afraid of being wrong? Okay, let's try again. How many of you think if I'm going to do the timing dynamically, so to determine when I'm going to do a task on the fly, determine which ordering I'm going to do the task statically, a priori, beforehand, and then assign which task to which processor on the fly as well. How many of you who thinks it's a reasonable way of designing? Excellent, more people with opinion. Fantastic. Who says it's not a meaningful way of designing? Okay, good. One of you among yourself who said it's not meaningful, can tell me why?
Pretty clueless, to be honest, but I just...
That's love.
Yeah. I just think it could be a lot of runtime errors or something if you set decisions at the start or something. And then,
Okay. Why do you think it's meaningful?
I figure you can sorry when the program is running, and if you decide some priorities, it's like how we do things in life. So you put priorities on the to-do list, and then when you're actually executing it, because of this and that, it may take more time to do a specific thing, but you will always complete that thing first before you move on to the next thing.
Now, the question on its own is an impulse question, because I didn't give you the full assumptions of what we know, what we don't know. Okay? To be able to answer any of these questions, first we have to know the assumption. For example, she alluded to a very important point, that if we have a list of the tasks that we are going to do, if we have that knowledge, then we can assign some priorities beforehand. But if we don't have that list, by construction, I cannot assign priorities.
Could you not still have like a dynamic priority assignment system where, like, for instance, your scheduling based on, you say you get multiple tasks that come in, then you then sort those tasks into a priority queue, and then those get executed on the process.
But that's my question predicated on the fact that I'm doing the priority ordering a priori.
Yeah, but like for instance, you could have like say a schematic which weights those priorities. So for instance, say you have two tasks that come in, and you have a priority system that says, hey, if this task is available, if these both tasks are available concurrently, then the one with the higher priority gets executed.
Sure.
So you can have like
You can have that,
In
but
that sense,
for
you're
that,
combining
you need
that.
to have the knowledge of what tasks are going to pop up.
sure, well, like in terms of like you need a list of tasks, right? In some sense, right? But you don't
Okay.
necessarily need to know what they are.
Sure, the assumption is that then you know exactly every task that is going to pop up. they just arrive not according to your list, a variation of that list, you have to come up with a different scheduler because you haven't taken into account for those.
You're saying there's a finite set of executable.
That you know a priori. Which is a reasonable assumption, but the fact is that we have to fix it. The other issue is it doesn't make sense to set the priorities, but then do the assignments on the fly. So that becomes a bit weird in the question that I asked from that perspective. Because if I know the priorities exactly and I'm assigning the priorities already, I might as well do the assignments offline. Anyway, it's good to think about these problems. It's very high level, but that's how we start. Thinking is the first step of understanding these things. Okay, now real-time systems. They come with all sorts of different timing constraints. They come with deadlines, which is really physical, clock-on-the-wall time that we need to finish a task. That's called a deadline. They come with precedence. So we have to do a task first to be able to do the other tasks. These are all the constraints that we have to deal with. And then any general temporal logic proposition. Temporal means related to time. Logic is logic. So anything that we can express as a temporal logic statement. That will be the focus of your next 2 lectures. How to state these sort of conditions. So really an example can be I only want a task to run for a certain number of times or a certain period of time after another task is carried out. And we use logic, temporal logic, and in a different language. We use the language of mathematics because natural language is by definition imprecise. And we cannot design functioning engineering systems based on imprecise language. That's why we write everything in terms of maths. That's another reason that as engineers, we study a lot of maths, hopefully. Okay? Now, a lot of you, when they see a title like this, hard real-time constraint and computing systems, might think that hard refers to it being difficult. But it's not. It really refers to the types of deadlines that we deal with in a lot of real-time systems. So when the deadlines are hard, so when we cannot violate them, if we violate them, something goes very wrong, we call them hard real-time scheduling. So that's the setup. We have soft real-time scheduling as well. That's when we really don't want to violate deadline, but we violate them, nothing bad's going to happen. But we want to minimize that violation. Okay. Now going back to that example of microkernel scheduler, it does different things again. It has to schedule threads or tasks. I'm going to use them interchangeably. Just interchange it in your head. It has to set up periodic timer interrupts. Last lecture, what did we call that period that the kernel interrupted? Huh? It had a nice name. TV. That's where the time between ISR interrupted. So in a Linux kernel, it's around 10 milliseconds. So we interrupt every 10 milliseconds, then we have to determine to do what we are going to do. It has to create the data structures and it has to dispatch a thread. So it has to complete the task. That's just the jargon for started doing what it's supposed to do. And then goes back executing the main thread. Remains idle, listens, etc., etc. The thread data structure contains all the states, all the machine registers, the addresses that we need to resume executing the thread, status of the thread, so it is blocked or mutually excluded, it is in a mutex lock. So what is the status? Should we go back to it or not? And then some priority and W set. W set, worst case execution time, is something that we are going to use a lot to do this schedule, be able to determine which task to do. If we can spend time on maybe 2 weeks on just understanding W set. But think of it as if I'm given a task, it comes with an estimate of how long it's going to take the processor to complete the task at the worst case. Processors, they are not deterministic, so they might complete the task quicker in one cycle or slower in a different cycle. So it's a worst case time estimate. And then we are going to dispatch a thread. We have to go through a process as well. First, we are going to disable the interrupt, so we are not going to jump out of it. We will determine which thread needs to be executed. So it's the scheduling part at any given time. If we don't need to switch to any new task, so for example, if we interrupted somewhere for whatever reason in the middle of another thread, and then we decided, oh, let's go back to the previous one, then we just return, nothing happens. If not, we have to save the state of the thread, so make sure that when we are coming back to it, we can resume, so we can continue from where we left off. Really save the return address, start the new thread, and then continue, repeat. That's really the process that we go through. Now, if you want to go to a party and talk about what you study at the university, if I can do this. So that's a very famous scheduler. You can look it up on Wikipedia. But that's a full kernel scheduler. It's not a real-time scheduler. Okay. Took us 20 minutes to get to where we are going to talk about. So in this lecture, I'm going to talk about some ideas called preemptive scheduling and non-preemptive scheduling, periodic versus aperiodic tasks, things that come with fixed priorities and dynamic priority. And then I will quickly mention different types of anomalies. For more information on anomalies, go and look up the chapter in your textbook or all the other references that I mentioned. But to be able to understand these, first we have to understand the common ways of solving the scheduling problem. Okay. Let's start with non-preemptive versus preemptive. If I have a non-preemptive scheduling, I never ever interrupt a task while it's being run. I never switch out of an active task. In a preemptive scheduling, I might interrupt a task that is being run midway to do something else, to make sure that I end up satisfying the constraint that I need to satisfy. That's the biggest difference. So either we preempt a task or we don't preempt it. If we can preempt a task, it's a preemptive scheduling scheme. So we might preempt a task because of a timer interrupt or because of an input-output interrupt. Again, depending on the scenarios, we can't really be sure. It really depends on the application we are looking at. We can do it when a new thread is created, just to make sure that we still satisfy, so a new task arrives, so we still satisfy the constraints that we have to satisfy. If some thread is blocked because of a mutex block, for instance, or a semaphore flag being down, if a semaphore state is changed, we might need to reevaluate where we are, or when the current thread calls for another OS call, so it really generates another thread. So file system access, network access, all of these things are OS threads that now we have to incorporate in our own scheduling. So for example, just to give you a feel of what precedence means, in this example, if I have some thread, call it A, calls a network access, we cannot go back and finish the execution of A until we finish the network thread, network access thread. So there is precedence. We cannot finish A before finishing the network access. Okay? So the standing assumptions are all assumptions have priorities. Either they are statically assigned or they will be dynamically assigned, so they can vary in different cycles, different times. And the kernel or the microkernel or whatever that handles the scheduling keeps track of which threads are enabled. So they can be executed either because of a lock or semaphore, all those things. What are the available threads? Okay? In a preemptive scheduling, at any given time, the thread with the highest priority is being executed, but sometimes that highest priority can switch. So we end up executing a different thread, a different task. So really, whenever the priority or status changes, we change the thread that we are executing. So really, what the term is, the first thread is preempted. Again, it's important to understand what all these jargony names mean, but don't get hung up on the words themselves. Understand the meaning behind the word, because you might see similar ideas in a different field of engineering. Those people came up with their own names for these ideas. So understand the meaning behind the names. Okay, now we are getting a bit more formal. We are going to hopefully use a bit of more maths to be a bit more precise, just not all the wishy-washy wordy stuff. So now we need to come up with better assumptions. So we are going to start with n task. This n is a variable, can change. So let's start with n task. We are going to assume each of these tasks are going to be done periodically. So every t units of time, I have to redo one of these tasks. For instance, task 1 is going to be repeated every t1 seconds. And when I say seconds, replace it by units of time, because it doesn't matter. Task 2 is going to be done every t2 seconds. Now these are variables, right? I could have changed the variables with omega 1 to omega n. These are variable names. Don't get hung up on the variable names. So if you go and look up your textbook, the textbook uses p. But don't suddenly get confused. Oh my God, these variable names are different. So this is a different concept. It's not. They are the same thing. Okay. So in the lecture, we are going to use t, t1 to tn. So we are going to impose hard deadlines, and we are going to I can have deadlines that are different from the end of periods. But for simplicity of notation, let's assume my deadlines are really the end of the period. So I need to complete task 1 by the end of this period T1. Task 2 by the end of this period T2. And then I go and repeat the whole thing. We start with the assumption that we have access to worst case execution time. So there are all these ways of estimating it. Let's assume we've done those estimations. And again, the simplest case, let's assume we don't have these blocking input-output boards, semaphores, mutexes. It is important in engineering to always start studying the simplest system that is reasonable, to understand it then make things more complicated. If you start with the most complicated system, you will never understand anything, and then you will just luckily randomly change things until something happens. So we are going to start this under these assumptions that make the problem tractable for us to understand what we are doing. So there is no precedence constraints. We assume the priorities are fixed, and we are going to think about a preemptive scheduler. One famous preemptive scheduler is rate monotonic scheduler. Rate refers to the speed that we have to accomplish a task. Monotonic refers to it being monotonic, so things should be in some order. So priorities are determined based on the period. So the task with the smallest period will have the highest priority. That's the monotone property of the scheduler. We order things, monotone increasing order. This is a result out of the 70s, 73. Under those assumptions that I just mentioned, we can state an important theorem. A theorem is a precise mathematical statement that is always true if the assumptions hold. Okay, and usually theorems, in case you haven't seen it before, take a format of logical statement P, then logical statement Q. Let's look at this theorem. So, under no precedence constraints and all the other things, if any priority assignment yields a feasible solution, so if I can come up with any priority that gives me something that works, then RMS, this rate monotonic scheduling, also yields a feasible solution. I'll come back to this theorem in a couple of slides. So here I use the term feasibility, but I haven't told you what it means. In this setup, we talk about feasibility to mean that every task is completed within its period. So we can achieve the hard deadlines. That's what we mean by feasibility. It is very important to define these terms exactly. Otherwise, again, we end up talking in vague terms that don't mean anything. So, in other words, all tasks meet the deadlines. So the statement says, if some scheduling is going to give me feasible schedule, RMS will give me a feasible schedule as well. And we can term this, say, statement like this: RMS is optimal with respect to feasibility. Whenever we talk about optimality in this subject or anywhere else, we have to always qualify what we mean. Because I can say Iman is the best person in the world, it is a true statement, but vacuous, because I haven't told you with respect to what. Because it's me. Okay. So, a scheduler that returns a feasible schedule for any task, task sets, for which at least one feasible solution exists, is called optimal. So that's how we define optimality with respect to feasibility here. Now, an example. Imagine I have two tasks. Task 1, task 2. They come with two different periods, T1 and T2. They come with two different worst case execution time, C1 and C2. Okay? So the question is that, is a non-preemptive schedule feasible or not? is it possible to come up with some ordering of these two tasks so we can always accomplish both of them before the end of the period?
C is the worst case scenario, so why is C smaller than T?
T is the period that we have to execute the task by the end of the period. C is the time that it takes us to compute the task. Okay. If I had dedicated processors for each of those tasks, then it would have been a feasible schedule. Now, if I have one processor, the question is, can I achieve it with a non-preemptive scheduling scheme? The answer is, I mean, it's simple to see. It's no, I couldn't. Because whenever I start completing this task, it's going to take a period, some time, that is longer than this. So by definition, I cannot meet my deadline for the second task. Okay? So we need to preempt. So this is what that. So now we need a preemptive scheduling scheme. So we are going to assign a higher priority to the red task, the task with the smaller period between these two, the smallest period ever. We order them, so it's here task 2 and then task 1. And then we start doing task 2 first. So this is the example. We start doing the second task, then we finish it, we switch to the other task, task 1. But then, at the beginning of the new period, we complete the red task. So now the blue task in this interval is preempted. After we finish that, we go back here and we repeat the process. So that's an example of a preemptive scheduling problem in RMS. We always start solving always carrying out the task with the higher priority, which is the one with the shortest deadline or the shortest period. Switch to the other ones, complete it, then preempt it accordingly. Very simple setup. What we are assuming is that zero time needed to switch between tasks. If there is a time associated with switching, then you have to have a bit of a buffer between each of the preemptions. But this allows us to understand the idea. Now, whenever I have a statement that is like P then Q, that statement has a contrapositive. What is it in terms of P and Q? Does anyone remember? Q, not P. I mean, not Q, not P. So it really, I mean, this is another way of reading these statements to understand them from a different perspective. So it means if we just, the contrapositive statement, which is the equivalent to the theorem, is if RMS fails to yield a feasible schedule, there is no other schedule that would have yielded a feasible solution. So if we cannot solve a problem with RMS under these assumptions, even God himself or herself couldn't solve it. The proof can be extended to arbitrary number of tasks. I just showed you a 2-task scenario that becomes tedious. It's just messy. It's not really inspiring, but it exists. There is a statement. There is a formal statement for it. We only talk about optimality with respect to feasibility. We might have other criteria. RMS doesn't address those criteria. There are practical implementation. We can have timer interrupted at some great common divisor of the period, or we can have multiple timers. It might have a negative impact on processor utilization. In a very hand-wavy way, the processor's utilization is the amount of time, the ratio of time that we are doing things divided by the total time. So we want to minimize the idle time when the processor is not doing anything. In RMS, might end up giving us a lot of idle time that the processor just doesn't do anything. There is another idea in scheduling called, let's go, I keep forgetting, deadline-driven scheduling. There's another thing called Jackson's algorithm. Came up in the 50s, and really the idea is this. If I have a bunch of tasks with a bunch of deadlines, I'm not talking about periodic stuff. Whenever a task pops up, it comes with a deadline. I use D1 to Dn to denote those deadlines. And I finish a task at time fi. Then I define this lateness. The lateness is the latest time that we are going to accomplish a task compared to the deadline. So hopefully we always get negative values for the lateness. So we never crash the deadline. So if we cannot find the negative value, it means the schedule is infeasible in terms of meeting those deadlines. And usually it's a bad thing. Sometimes when we are dealing with soft constraints, we might be happy with some small positive values for the lateness as well. And really, the EDD algorithm tell us to execute them in order of non-decreasing deadlines. So we always do the task with the closest deadline first. It's a very intuitive thing. Usually these algorithms, for those of you who might be interested in a bit of math, hopefully a lot of people, I don't know, they are called greedy algorithms. We make decisions greedily. Okay. Jackson's algorithm really doesn't require preemption. We order the task based on the deadline, we start doing them in order. We don't need to switch necessarily for the Jackson's algorithm. I'm going to talk about the top two, this part soon, but let's look at the statement. Again, under the same type of assumption as before, EDD is optimal. This time, in the sense that it gives us the smallest maximum lateness among all possible schedules. So again, we are saying it's optimal with respect to a different thing now. It doesn't always give us a feasible solution, but it gives us the best it possibly is, the best that is possible without preemption. Now, why is it the case? This is the proof. Imagine we used a non-EDD schedule and gave us an ordering of a task that we first do task A, even though its deadline is farther away. It's a non-EDD schedule because we didn't do the closest deadline first. I can always switch the order of these two tasks. Completion times of the bundle is the same, but then I can define Lmax. By construction, maximum of these two values is FB minus DB because FB is larger than FA and DB is larger than DA. If I switch the tasks, I can come up with a new lateness for at least this pair. And then there are two scenarios. In both cases, it's really basic algebra. Think about it, you can ask the question. We always show we are not going to do any worse than this non-EDD schedule. And I can go through any other pair in the order as well, apply the same idea. So an EDD answer, EDD schedule, is not worse than any other schedule. Thus, it's the best we can do. Because I cannot find any other schedule that performs best. 20 years later, Horn came up with an idea to allow a dynamic way of doing it. So, some idea of preemption. The moment the task arrives, we have to now reconsider the schedule. That was Horn's idea. So again, the key is here. At any instant, we execute the task with the earliest deadline. Again, I've put all these references if anyone is interested. We can apply to periodic tasks and aperiodic tasks using these sort of ideas. It's a dynamic priority scheduling algorithm because when something pops up, we assign a new deadline to it. And in periodic tasks, a task might receive different priority in each period, depending on when do we want it to be completed, or when it's being invoked in the middle of its own period. In the simplest case, the deadline is at the end of the period, but we can have specific deadlines that are different based on the start of the period as well. The idea is the same. So think about it, then we can discuss it if you have any questions. Now, if I go and compare RMS and EDF, RMS was good because it's very simpler. An EDF schedule must maintain a list of ready tasks. So always keeping all of the tasks available to it. EDF, on the other hand, is optimal with respect to lateness, and it is practically much more desirable in terms of the properties it has, practical properties. So it's more efficient without getting into details. The system performs better under EDF. We can have that full utilization idea. EDF in general results in fewer preemptions, and when I talk about EDF, I'm talking about Horn's version of EDF here. And then we don't need to switch as much, because again, switching will require some time and resources to be allocated to the task. And deadlines can be different from the period. It doesn't need to be the end of the period. It can allow us to do different things. Now, let's talk about precedence constraints. We used a tool from discrete mathematics called directed acyclic graphs, DAG. So the way we construct these sort of graphs is all the children rely on their parent to be able to be executed. So the parent needs to be executed first, then we can execute the children. Well, that sounds terrible. But there is no way out. So leaves, okay. Roots and leaves, that's another way of looking at it. Okay, if I have a precedence structure that looks like that, with I'm assuming all the computing times, all of them are equal to 1, and with all these different deadlines, if I use EDF, for instance, I might end up with this schedule. So do this first, then do this, then do this, then go and do 4. It's very easy to see 4 won't meet its deadline, because it takes 1 unit to do here, so time 1, another unit to accomplish task 3, another 1 unit to accomplish task 2, but then when I get to task 4, the deadline was already passed. So if I use EDF, I will get that schedule. So it's not feasible. Can I come up with a feasible schedule? The answer is yes. There is an idea called latest deadline first scheduling. We start at the end. So we start from a leaf node with the latest deadline. So for example here, we allocate it first, and we move backwards. Now, we did this. The next is this guy. I guess I have, oh yeah, here we go, animations. So from the remaining nodes, we allocate 5. Remaining nodes, we allocate 3, 4, and we go backwards. LDF will satisfy all the precedents and will meet all the deadlines. Also, it will minimize the maximum lateness as well. But it has a problem. The problem is that when a new task pops up, we have to redo the whole thing. So that's the drawback. In engineering, there is no silver bullet. There are always trade-offs. LDF doesn't require preemption, so it saves us from the switching. But as I said, it really cannot handle things as they arrive. But we can modify EDF to address this issue, and it's called EDF with precedence or EDF star. Very recent development in the time frame that we are talking about. In the 90s, people came up with this scheduling. It relies on adjusting the deadlines. So taking into account the precedence as we compute the deadlines. How it works is, the equivalent. So let's talk about this slide. So we start from, for each task I, we construct a new deadline, modified deadline d-i, by looking at its neighbor's deadlines itself and its neighbor's deadlines minus the time that is needed to compute those deadlines. So we really want to bring the information forward in the tree. So if I have a child that requires some computation time C that to meet the deadline, if that deadline becomes smaller than my own deadline, I will adopt that value to pass information upstream. Okay? And then if you apply simple EDF on these modified deadlines, we are golden. We have the solution. Now, as tasks arrive, we have to reevaluate these modified deadlines, but then we can do the planning forward in the tree. So it's a bit better than LDF. The planning is not done backward in the tree. Again, EDF with precedence can be shown that minimizes the maximum lateness. Some observations. Timing behavior under all known task scheduling strategies is brittle. So when brittle has a meaning, it means small changes might lead to big changes, overall changes that were unforeseen. It is related to the idea of robustness in dynamical systems. So if I perturb things a bit, I don't want the output to change a lot. But scheduling algorithms, by the virtue of them coming from a particular branch of mathematics, they are brittle. They are not usually robust to variations. So it is a challenge. They are and the source of these sort of variations are in priority inversion and deadlocks. For example, if I have a high priority task that needs to access a register, but at the same time that register is being locked by a lower priority task, the high priority task is locked out of processing. So it's called priority inversion. The lower priority task will take over. It's a bad thing that happens. There are examples of it as well. In your textbook, the example that is given is from Mars Pathfinder rover in the late 90s. A similar thing happened to it. The other important fact is that performance improvement at some local level might lead to degradation in the global level. And that's the pitfall whenever we